Let's begin. Welcome back. Hope you had a good long weekend and you labored on the homework assignment, which you didn't, but some of you did. I saw this yesterday and I thought I'd share it with you. I'm not saying you are on social media 8 hours a day. You know, when your phone reports to you, you spent 8 hours on Instagram or Facebook and whatnot. But I thought, just a reminder that not everything you see on Facebook or Instagram, your friends, your kind of colleagues, college schoolmates, they're showing just the best snapshots of years of their life. So, oftentimes there's trouble on the other side. Okay, so last time I wanted to give you, we left off by starting a discussion on wanting to solve a large system of equations. So far, we know how to solve any system of equations. Small or large, might be costly if it's too large, but it can still find a solution. So we know how to do that. And we're doing it for these conservation of mass problems, relatively small number of equations, 10 maybe. You derive them by hand, you put them in. For the sake of illustration and also for later lectures by the end of the semester, getting you ready to solving differential equations, I want to give an example on where you would get a large system of equations and how those equations show up in a recursive form. In other words, unlike what you were doing in the homework assignment where you have to look at room 1, okay, what's the balance in room 1, room 2, etc. For problems that you will face in practice with differential equations, the governing equation, the governing linear algebraic equation in every compartment is going to look the same as every other equation. It just has a difference in indexing, 1, 2, 3, 4, 5, etc. So instead of balance between compartment 1, 2, and 3, then the next one will be a balance between 2, 3, and 4, and so on and so forth. So it becomes fairly consistent, and then you can build a very large coefficient matrix within a few lines of code without having to code each and every equation like we had to do so far. And the best example I like to give is a one-dimensional heat transfer problem. I choose heat transfer rather than mass transfer. Although they're similar, there's an analogy between heat and mass transfer. Mass transfer gets a little bit more complicated. Heat transfer gets complicated in other ways. But the basic idea of heat and mass transfer, the idea of diffusion, is similar. But heat is a little bit more intuitive to connect to, because we've all burned ourselves, our fingers and stuff. So, we have an intuitive relation with fire, right? Just fire, so elemental, so natural. And I started with a side note last time that the same way we can approximate a first derivative, we can also approximate a second derivative with this formula. Don't worry about these now. I will discuss those later once we hit boundary value problem discussions. But anyway, just know that there is a way to approximate first derivatives, approximate second derivatives, third derivatives, and so on. And don't worry too much about this right now, how I'm applying this. You might have taken this, or you might have seen it, or you might have taken it with me earlier. That's great. But for those who haven't seen it, just know that there are formulas to approximate first, second, and third, etc., any derivative. And the problem setup is as follows: we're going to consider a one-dimensional system. I call it a rod or a piece of material. Again, I like to give the example of the wall. This is drywall. There's a gap in. No, this is not drywall. Ouch. There's probably drywall over there. There's insulation between the inside and the outside. The outside is at a temperature, the inside is at another temperature, and you're trying to understand what happens to the temperature inside the wall itself. Okay? Or take your double glazed windows, you have temperature on the outside, temperature on the inside, and heat is being transferred in between. Okay, so that's the problem setup. What we want to do here is we're going to fix the temperatures on the left side and on the right side. So I know these are information that are given to us. We know them for certain. Okay, so t left and t right, or t at x0, t at x equal L. And that's the length of this one-dimensional problem. For also the sake of the argument, and this is just one example of a setup, is I'm going to heat or cool this object somewhere maybe in the middle, maybe 1/3 along the way, maybe 2/3, somewhere over here, and I can control what this heat looks like. It could be very wide, it could be very narrow, it could be just like a small lighter or match, or it could be a torch, right? So, or it could be a heating element that you somehow was installed in the wall, or an electric wire that is being overheated. So we have control over understanding what this source looks like. Now, the governing equation for temperature, or the balance of heat in this rod, can be expressed in terms of temperature, or in this material one. The governing equation looks like this. Second derivative of the temperature is balanced by -1/k times this source term. Okay? If you don't have a source term, this would be 0. This would still describe heat transfer in a material with constant conductivity, which I'll discuss in a second, and at fixed temperatures on both ends. We're going to come back to that point in a bit. K is called the thermal conductivity. The larger the value of K, the faster the material is going to move the heat along the material. Okay? So if K is very large, you're going to see that the heat coming from the heat source spreads very quickly, or the cooling effect is going to draw the heat out very, very quickly. Now you could think this may be an air dryer, for example, or a blower, right, trying to heat it or cool it. If K is small, then the material is going to resist heat being spread along the rod. Okay, it's going to resist that. So keep that in mind. Large K, small k. I gave the example last time. Air has a very small thermal conductivity as opposed to water, as opposed to oil, which has a much higher thermal conductivity. Then you go to steel, for example, or then ceramics. They have even larger Ks or smaller Ks. So different materials have different K properties. That's the thermal conductivity. You've taken heat transfer, I assume, in undergrad, as a quick reminder. But eventually, I'm interested in deriving these equations, which the courses next year will discuss. We'll discuss those more. We're going to touch on them by the end of the semester. Again, I don't want to get too involved in the physics in this course. Now, our goal is to find this temperature distribution numerically. Obviously, you might have a way to solve this analytically. This could be solved analytically, especially if S is linear, even if it's a little bit nonlinear in X, because second derivative, you integrate it twice in X, and you just find the double integral of S, and that's your analytical solution. But assume you don't know that. You're just going to want to put it in Python to compare also possibly to your analytical solution. When I taught this, my students were taking ODEs at the same time. So they were learning analytical solutions to this, which can be really nasty, long solutions. But then they would come and tell me, look, we did this in class, and then we solved it using the numerical method that we learned here, and they were able to verify that their analytical solution is consistent with the numerical solution rather than the other way around, because they had doubts about their ability to get the analytical solution. Anyway, K is given in units or dimensions of energy over length by temperature, or units watts per meter Kelvin. And the source term is a volumetric source term, is watt per cubic meter. Okay, so we've done this. We're good. Okay, now to solve this problem on a computer, and again, you've seen this. It's fine. Just bear with me. For those who have seen it, it's an opportunity to get you up to speed with what we do here. So to solve this problem on a computer, we are going to subdivide this domain, this material, into points. Okay, we're going to call this the grid or the mesh. And here for an illustration, I'm going to put 6 points. So I'm going to put a point here, here, equally spaced. So I'm going to take this entire rod or material and equally subdivide it into equal intervals. I'm going to do 5 equally spaced intervals, or 6 points. So 1, 2, 3, 4, 5 intervals, 6 points. Okay? And I'm going to place the points in between these intervals, because I want to put a point here and I want to put a point here. Why? Because I know I know the temperature at these points, so that's going to be an input that I'm going to use to find the temperature at these points in the interior. Now the spacing, we're going to call that spacing delta x. It's a constant spacing, so delta x doesn't change. And then we will assign a variable at each one of those points. We will index them from 0 because Python is indexed from 0. So at the first point, I'm going to assign t0. Now I know that t0 is equal to tl, so that's a given number to me. And then t1 for the next point. I don't know what t1 is. I don't know what t2 is. I don't know t3. I don't know t4, and so on. You could put 1,000 points. Doesn't matter. But the example here is with 6 points. And then finally, t5, the last point, is given to me by tr, or t at l, t at the right-hand side, the right side of the material. Okay, now my objective, when you solve this analytically, you get a temperature distribution throughout the entire material. It will be a function of x, e to the minus x squared, right? For any value of x, you can find the temperature. Here, numerically, I can't do that. I have to solve it at discrete points. This is why this is called grid, mesh, or discretization. Now, from now on, I'm going to call this grid or mesh. Use those interchangeably when I tell you, okay, show me the grid points on the material. You know what I'm referring to. I'm referring to these points. You got to draw them. Okay. Later, you will learn how to convert a continuous ODE, which is still that governing equation that we talked about, this guy over here. This governing equation, come on, this governing equation applies everywhere inside this material. So this governing equation applies at every point, including specifically the discrete points as well. So later you will learn how to convert that equation into an algebraic equation at every point. I'm going to give you the recipe here, but I'll dig a little deeper later into how to do it, and we'll do it together. But for now, you should know that for any grid point, so if I had 1,000 grid points or 1,000,000 or n grid points on this domain, that at any point inside this domain, inside this material, the differential equation can be converted to an algebraic equation. So I'm going to take a representative point, call it I. This is some arbitrary point in any point in the middle. And I'm going to take this equation and apply it at point I. Because this equation is valid everywhere, it should be valid at point I. So in other words, I'm going to take second derivative at I equal minus k s of x at I. Now I'm going to convert this using the formula for second derivative. Don't worry about this step, because I will give you the formula. Okay? And then I convert this continuous ODE into an algebraic relation relating ti plus 1, and ti minus 1, okay, to s of xi. I still don't know what the ti's are. That's what I'm after. But that's the whole idea. I'm building a system of equations that involves all of the ti's, going from 0 to n. Right? Then if I rearrange this, I know s of xi, because I know s, it's an input. I know k, I know delta x. I can rearrange this equation so that it looks like this. Okay? So right now, at this point in the semester, I will give you this formula. I will tell you this equation of heat transfer looks like this when you convert it to an algebraic equation. Okay? So now this applies at any point I in the domain. However, at the boundaries, we know what the temperatures are. So T0 is known, is given to us, and Tn, that's the last point, is given to us. But anywhere in between, this is the formula that applies. So for example, for point 1, when I is equal to 1, then I have Ti minus 1, that's T0, minus 2T1 plus T2 equal minus delta x squared times S at x1 over k. We haven't defined what this means. Just bear with me for a second. A lot of symbols right now. What you have to recognize here is that this recurrence formula is the same at point 1, point 2, point 3. All you have to do is just substitute the indices correctly. Okay, so for point 2, when I equal to 2, I put I equal to here. I get T3 minus 2T2 plus T1 equal whatever, right? So T1 minus 2T2 plus T3 and etc. and so on. Okay? You might not see it yet, but we are building a system of equations for all of those T's that are unknown. Now, I have not defined S of xi yet. Okay? What is S of xi? Well, it's pretty simple. Just the same way we assigned a temperature value for each one of those points, each one of these points also has a coordinate value because it lives on whatever coordinate system I defined. I said this is x equals 0, x equal L. So every one of those points, I know the values of these x's. I know the value, this at x0, this is 0, at x5, this is L. And at every one of these x's, I know what the value is. So for example, if L is equal to 1, then my delta x is 1 over 5 because I divided the domain into 5 intervals. I decided to do that, right? So the interval size is L over 5. That's my delta x. Then I know if x0 equals 0, x1 is equal to delta x, x2 is x1 plus delta x, and so on and so forth. 3 delta x, 4 delta x. I know the value of delta x, which is 1 over 5. So I know exactly what the x values are going to look like. Okay. Now, in Python, this is doing it by hand. Right? In Python, it's really, really easy to do this. So I want you to get your Jupyter notebook so we can do it together. And we'll start building this solution step by step together. In Python, this is done with something called linspace. Linspace is a routine in numpy that subdivides an interval into equally spaced interval, or subdivides a length into equally spaced intervals. This is exactly what I want to do here. So let's do it together. It becomes clear. Get the Jupyter notebook up and running, please. And okay, so let's call this, move this over to the Crestone. Okay. So you're noticing there's not a lot of theory going on in the first part of the course because I need to build your tool set so that when we get to the more serious stuff, you are ready to start solving more complex problems. All right, so let's call this fall 2025 heat transfer example in class. Okay. Can you guys see in the back? Maybe I'll zoom in. So I'm going to import numpy as np. And for the linspace, I'm going to just simply call np.linspace. So let's first define my L is equal 1. So that's in meters. Okay. And then if I say np.linspace from 0 to 1, okay, if you look at linspace, you press Shift Enter, it tells you return evenly spaced numbers over a specified interval. So by default, it only needs 2 quantities, start and stop. So we're going to go from 0 to L, but it defaults to 50 points. What if I want 5 points or 6 points or whatever, right? So we can change that simply by saying, okay, if you come back here and you say num is equal, let's say 2 points, okay? So if I split this into 2 points, it's just going to give me 0 and 1, right? The endpoints. So this is not referring to the intervals. This is referring to the number of points, not the number of intervals. Okay. So so this would be one interval essentially. For 2 intervals, I need 3 points. Then look at that. It's going to give me an array that contains 0, 0.5, and 1. So 0 is the leftmost point, 0.5 right in the middle, and the last point is 1. Okay. So remember, linspace takes the number of points, not the number of intervals. Okay, so for our problem, we needed 5 intervals or 6 points. So it will give me all of those. Now, what if I can call this my x values or xi's, right? And that would be the xi in S of xi. Okay? Very simple. That's all I need to do. All right. So I'll resume. Okay, so now that we've defined our x values of these discrete points, because they have coordinates, okay, now I can simply evaluate S of x, because S of x is a continuous function of x that's usually given to you continuously, as we will do in this problem. And then you can evaluate it at any x value, specifically the x values that correspond to those discrete points. And for simplicity, I'm going to call S of xi, I'm going to call it Si, S subscript I, for simplicity. So similarly, the same way we had x1, x2, x3, t1, t2, t3, we do have s1, s2, s3, s4, s5, and s0. S0 and S5 are going to be irrelevant because we have boundary conditions there. We know the temperature. I don't care. I'm not solving the equation at those endpoints. But still, I can define S at all of those points. So for example, if S is equal e to the minus x squared, then simply S1 is S of x1, and that's e to the minus x1 squared. What is x1? It's what we built in the Lin space just a minute ago. S2, same thing, e to the minus x squared 2, and so on and so forth. Okay? Now, to generate an array of S values, so I need to generate an array of S values because this is going to be a system of equations. I need to know S at every point because for each equation there's going to be an S value. Remember what I said about numpy. Numpy operates on arrays. So a function, a mathematical function from numpy can operate directly on an array. And I already have the array of X values with the Lin space, agreed? So I can take any numpy function, and remember function means math function, and apply it directly on that array, okay? So let's go ahead and try this. Let's go ahead and try this. So let's say define source of x. Then I'm going to do return minus mp.exponential minus x squared. Okay? So I'm defining a Python routine that computes a source term. I'm calling it source term, source. Given any x value is going to return e to the minus x squared. It can take a single x value or an array of x values. If it takes an array of x values, it's going to apply this formula to every entry in the array. So if I were to do source of xi, what is it going to return? A single value. So xi is defined up here. It's an array of x values along the material. What is source of xi going to return? An array of what? Containing what? The source evaluated at each one of those xi values, right? So this first point is my source term evaluated at xi equals 0. This one is my source term evaluated at 0.2. This one is my source term evaluated at 0.4, and so on. And there's 1, 2, 3, 4, 5, 6. There's 6 S's. There's 1 S at each one of those intervals. Okay, very good. Now we can get back to business. So we took a little detour just to define what S of xi is. So now that the coordinates and source terms have been defined, we can really define the governing equations for all the unknown temperatures. Okay. For each one of those blue points, there is a linear algebraic equation that relates the temperature at the two neighboring points to the temperature at that point. So remember, our generic formula for the temperature in the rod is Ti plus 1 minus 2Ti plus Ti minus 1 equals some known value. This formula is relating the temperature at point I to the temperature at point I plus 1 and the temperature at point I minus 1. So what it's telling us is that the temperature here and here and here, they're kind of tightly related to each other. And then for every point, that's how it is. For T2, We have relation between 1, 2, and 3 for T3, and so on and so forth. So think about the compartments of mass conservation you're looking at in the homework, or we did in the example in class. Compartment 1, 2, 3, and so on. In those cases where the system was small, you had to do it by hand, figuring out the balances at each point. Here, the balance is generic. Okay, it's the same balance at every point. You just have to reproduce it over and over again. So let's continue with the math. For point 0, I know that T0 is given to me as TL. So this is a given value. I know this value. This is my input. For point 1, again, this is T0 minus 2T1 plus T2 equal minus delta x squared times S1 over K. We know S1, we know delta x squared. Normally, you might be inclined to say, well, Professor Saad, I know T0. Let's move it to the right-hand side. You won't be wrong in doing that. But then later on, your solution will not contain 2 zeros. So when you plot it, you're not going to have the boundary points involved. So what I like to do, I like to include the boundary points in my system of equations. Okay, so this would be T0 equal TL. And pretend that I don't know what T0 is, but it's coming from this equation, so that when I have my solution, it returns the solution even at the boundary point. So when I plot it, I plot from boundary to boundary. Okay, just a little trick for simplicity, for convenience. Okay, so then at point 2, I have this equation. Okay, go ahead and write the equations now for point 3, 4, and 5. Okay, continue writing for point 3, point 4, and point 5. Just do it real quick on your laptops or on your note sheet. Just apply the recurrence formula at point I equal 2, I equal 3, and then at I equal 5, we have information already, so we don't need to apply that recurrence formula there anymore. Okay, so what is it at point 3? Mm-hmm. S3, that's correct. Yep, don't forget the S, that's correct. And then same thing at point 4. Okay, you have T3 minus 2T4 plus T5 equal minus delta x squared times S4 over K. And then for point 5, T5 equal TR, right? T right. I love to hear your voice, okay? Okay, so now we have just, look, we started with a differential equation that we probably didn't know how to solve. But now I have a system of algebraic equations. There's no derivatives, so they're algebraic. What are my unknowns? They're T1, T2, T3, and T4. You could say T0 and T5, but T0 and T5, they're given. But all of these unknowns, they show up what? How do they show up? Linearly, non-linearly? Linearly, they show up linearly. Look, you go home and repeat this exercise, okay? You're gonna go home and you're gonna repeat this exercise. There's no rocket science here. There's no magic. This is, I teach this to my undergraduate numerical methods. So if they can understand it, you can understand it. Okay, it's not that hard. It's just a system of equations. All the equations, they show up, all the unknowns, they show up linearly. So this is a system of linear equations. Do we know how to solve systems of linear equations? Yes, you bet. Yep, definitely we do. Okay, is this a well-posed system? How many equations do I have? I have 1, 2, 3, 4, 5, 6 equations. How many unknowns do I have? T0, T1, T2, T3. Oh, what is T4? I have how many unknowns do I have? T0, T1, T2, T3, T4, and T5. 6 unknowns, 6 equations, so it is well-posed. Okay, so I have as many equations as I have unknowns. Okay, now, again, do not worry how we got these. I'm going to give you the recurrence formula, but you should know how to apply it. You should know, again, I'm just going to take the formula with i's and I minus 1, I plus 1, and apply it at every point, so I can derive my system of equations like this. Okay. Now, just pay attention to how the equations at the boundaries are different. In fact, mathematical theory tells us that you only get unique solutions for differential equations once you specify initial and boundary conditions. In the absence of initial and boundary conditions, there are no unique solutions to differential equations. So here I know I will get one and only one solution that given that I've specified my boundary conditions here. Now the next step is to elevate this, because obviously this becomes tedious and annoying to write, because I'm not going to do this for 5 points. I'm going to do it for 1,000 points to get an accurate solution. I'm not going to write this 1,000 times. But if I learn how it works for a few points, then I can generalize it for any number of points. So now we can try to write these in matrix form. That's what you're going to do next. So you're going to take as your solution vector T0, T1, T2, T3, T4, and T5. Put them in a column and build me the coefficient matrix on the right-hand side. Go ahead. And don't look at the slides from Canvas. Yeah, so this is the layout of my solution vector. It makes sense because I'm starting from left to right. I'm not going to jumble them. I'm going to put them in that order. First equation solves for T0, second equation T1, and so on. So start with the solution vector and start building that coefficient matrix. Think about what should the size of that matrix be. I have 6 equations, 6 unknowns. And don't forget the right-hand side. Okay, if you have an answer, volunteer. Let's start by asking, what's the size of the coefficient matrix? 6 by 6. Okay, what's the first row? A bunch of zeros. Okay, and then times T0, and then on the right-hand side, TL, correct? Okay, what about the second row? So that's the second equation. Other contributors? And a bunch of zeros, okay. Do you see a pattern in the coefficient matrix? Okay, what does the pattern look like? Diagonals, bunch of diagonals, okay. Okay, so if you've done this right, this is what your system of equation looks like. Your coefficient matrix has 3 non-zero diagonals mostly. Everything else is 0. There's your main diagonal. It's mostly -2, but there's one at the beginning and one at the end. Why? Those are the boundary conditions. This is saying 1 T0 equal TL and 1 T5 equal TR. So when you solve it in numpy, it's just going to return T0 equal TL, T5 equal TR. That's why I include this in the coefficient matrix, so my solution contains the boundary points. But then it's -2 everywhere in the middle, and then there's 1s on this diagonal and 0 at the end here, and 0 at the beginning of this diagonal, and mostly 1s. So there's mostly 1s on this first upper diagonal, 0 at the beginning, and mostly 1s on the lower diagonal, and 0 at the end. Now, only when you write it in matrix form do you see this pattern. Would you trust that this pattern is going to repeat and be the same for any number of points I put? So I put 100 points or 1,000 points. Okay, what's going to happen? I'm going to have the same pattern. The same pattern, even at the first point and the last point. Those are going to be fixed, but everything in the middle is just going to be replicated. The only thing that will change is just this first one and this last one. They'll stay 1 at the end, but everywhere in the middle, you're just going to add more and more equations. On the right-hand side, same thing. First and last terms, they're the boundaries. And all in between is that delta x squared times s at whatever point you're at over k. Okay? This is super useful because now I can ditch all of this and simply work with the coefficient matrix. Because this matrix is programmatic. In other words, there's a pattern in it. And I can tell Python to build that pattern very quickly. We're going to learn. That's what I'm going to teach you here. To build it really quickly. And what you should take is just what the matrix looks like. Okay? In general, as I increase the number of points, I put n points, or for total going from t0 to tn minus 1 or tn, whatever you want to, however you want to call it. But the first point is always 1, 0, 0, 0, and the last point is a bunch of zeros and 1. But then I have 1 minus 2, 1, and then shift, 1 minus 2, 1, and then shift, 1 minus 2, 1, all the way across all of those points in the interior of the domain. This is really cool because I can scale this now. I can write one code that I can provide with, hey, solve this problem with 100 points. Solve this problem with 1,000 points. I don't have to change anything except n, the number of points. Okay. Now, what kind of matrix this is? When we talked earlier about the common types of matrices, this is called a tridiagonal matrix. There's 3 main diagonals that are non-zero, mostly non-zero. You say, well, there's a 0 here, Professor. Yeah, okay. It's 1 0 out of thousands of non-zeros on a diagonal, okay? So, but they're mostly non-zero, these diagonals. This is called a tridiagonal system of equations. This is called the main diagonal, first upper diagonal, first lower diagonal, with respect to the main diagonal, okay? Now, something cool happens now, and I'm going to go through this analysis a little bit with you. For n points, in other words, n equations, what is the size of the matrix and the size of each non-zero diagonal? So what's the size of the matrix? If I had 6 points, the matrix was 6 by 6. If I have n points, n by n, right? N by n. N equations and unknowns. Rows are n rows times n columns. Okay. What about the size of each of these diagonals? How many entries do I have in this main diagonal? Just talk in terms of n. So yeah, if it was 6, then for n points, it's going to be n. What about the first upper? It's 1 less, right? Because as you traverse all the way to here, you drop 1 term, right? So you think of it as, okay, this main diagonal corresponds to n entries on the solution vector. First upper corresponds to n minus 1 of these entries. What about the first lower? Also n minus 1. Okay, that's important because that's going to help us build this pattern very nicely in Python. This is also what we call a sparse matrix. What is a sparse matrix? A sparse matrix, first, a sparse matrix is one that has a sparsity more than 50%. So what is sparsity? Sparsity for a matrix is defined as the number of zero-valued entries divided by the total number of entries in the matrix. In other words, what is the portion, what is the fraction of all the 0 entries in the matrix? Okay? In other words, and I'm going to neglect this 0 and that 0 because they're insignificant for large n. In other words, if I were to count all of these zeros here and all of these zeros here and divide them by the total number of entries in the matrix, which is n squared, that's going to give me sparsity. That's going to give me a measure, a quantity called sparsity. And it's a fraction. It's a percentage. My answer could be 50% or 40% or 80%. What does it mean? It means 80% of the entries in the matrix are 0. If my sparsity is 40 or 0.4, 40%, it means 40% of the entries in the matrix are zeros. Yeah? A matrix is defined to be sparse if the sparsity is greater than 0.5. In other words, if more than 50% of entries in your matrix are 0, then we call that matrix a sparse matrix. If less than 50% are 0, then it's a dense matrix. It's not a sparse matrix. Yeah, it's just an arbitrary definition. Okay. Now, sparse matrices are important for heat transfer, fluid mechanics, mass transfer problems because they show up all the time. In computational physics, we deal almost exclusively with sparse matrices. I will talk about the issues with sparse matrices later in that you're going to, very simply, you're going to commit a grave memory error by storing all of these zeros, although they are all zeros. They don't matter. Well, they matter in the solution, but for storage, why do I need to store the same value where I know that that's going to be 0? Okay? So this is going to have big implications on matrix storage. Okay, so now I'm going to take this tridiagonal system, and for a general tridiagonal n by n matrix, I want you to develop a formula for the sparsity of the matrix. Okay? Assume all of the entries on these diagonals in green, assume all of them are non-zero. So don't assume there's no zero here or here. Just tridiagonal, all of the three diagonals are non-zero. Everywhere else it's zeros. Build the formula for the sparsity of this tridiagonal matrix. So in other words, count. So you have your total size of the matrix is n squared. Now I want you to count all of the zeros in this region and in that region. Now remember, you know how many entries you have here, here, and here. So so you can count the non-zeros if you want. Give it a try. So again, sparsity, I want to count the number of zeros in the matrix and divide it by the total number of entries in the matrix. Thought you had a question. Give it a try, please. I'll give you some light. So one trick to get this done is, instead of counting the zeros, you already know how many non-zeros you have. So if you count the non-zeros and subtract that from the total, that gives you the number of zeros, right? Because we know the size of the main, first upper, and first lower diagonals. Yeah. So the size of the main diagonal is n entries. First upper is n minus 1. First lower is n minus 1 as well. I mean, you could say, these guys here, you have n minus 2 plus n minus 3 plus n minus 4 all the way to n minus n plus 1, okay? And then add all of that up. That's like a Gaussian sum times 2. Or you can count all of the non-zeros here, which is only 3 diagonals, and subtract that from n squared. Nothing? Anything? You got a formula? Okay. Okay, what's your formula?
Just n squared minus 2 times n minus 1 minus n divided by n squared.
Yeah. Okay. All right, so the total number of entries is n squared. The main diagonal has n entries. The first upper has n minus 1 entries. And the first okay, let's do this right. So the first upper and first lower, they each have n minus 1 entries. So the total number of non-zero entries is n plus n minus 1 plus n minus 1. Agreed? I'm adding the number of entries in the main, first upper, and first lower. So that's 3n minus 2 non-zero entries. Everything else is 0. So what's the number of zeros? It's the total entries in the matrix, n squared, minus the amount of non-zeros. So that gives me the number of 0 entries. Sparsity is that number over n squared. So n squared minus 3n minus 2 over n squared. Now, for this system, for this material heat transfer problem, if I had 100 points only, what do you think the sparsity is? 50%, 60%? Just don't punch it in. Give me a number. Just 100, n equal 100 points. That's nothing. 100 equations. what do you think the sparsity is going to be? How many, what's the percentage of 0 values in the matrix? 90%, 95? Okay. 80%? It's 97%. Okay, it's 97%. In fact, as n approaches infinity, the sparsity will approach 99.99%. So for 1,000 equations, your sparsity is going to be 99.9%. So the vast majority of entries in your matrix are going to be zeros. Okay? We will see later that for as little as 64 points in 3 dimensions, if you store all the zeros, it's going to take 512 gigabytes to store the matrix. Okay? And there are smarter ways to store these matrices. Anyway, so I digress. That's a detour on sparsity. Just that's it. We're not going to dig deeper into sparsity. If you take my CFD course, we will be working with sparse matrices almost every day. All right. So now we'll go back to our system of equations. We've forgot the differential equation. We forgot the discrete formula. All we're working with, as far as I'm concerned, is a system of linear algebraic equations that has a pattern. Okay? And you want to be able to build this coefficient matrix for any number of points on that heat transfer problem. So we need a mechanism in Python to create these to create these large matrices, to scale it for any number of n. Again, I don't want to use Python as a calculator. I want to write one code that solves the heat transfer problem with 10, 15, 100, 1,000, 10,000 points, okay, and give me the temperature distribution. And I want to write one piece of code to do that. So I need a mechanism to build this pattern in the matrix. Okay? So luckily, most entries are repetitive, like I said, except for the points at the boundary. But most of the entries are -2 here. Most of the entries here are 1. Most of the entries here are 1. So, you know, it doesn't seem like that complicated to build this. So here's the idea. What if we can create the non-zero diagonals as one-dimensional arrays? So I'm going to go and tell Python, create an array of size n that has -2s in it, and then fix the endpoints. Create an array of size n minus 1 that has 1s in it, and then change the last point to 0. Create an array that has mostly 1s in it, of size n minus 1, and fix the first point to 0. And somehow take those 1D arrays and put them in a matrix. Just turn them and put them as diagonals in a matrix. Python provides exactly that for this purpose, for these types of matrices. So the step 1 is to create the 1D arrays. We know how to do this. This is numpy.array. But also, you don't want to go and put 1, 1, 1, 1, 1, or -2, -2, -2 n times. That defeats the purpose, right? So there's a really cool routine in NumPy. It's called numpy.ones. Ones gives you an array of ones, just one, that repeat how many times? N times. So np.ones of size n, it creates an array of size n that contains only 1. So np.ones 3 is going to give you a numpy array that has 1, 1, 1, 3 times. np.ones 5 is going to give me an array that has 1, 1, 1, 1, 1, 5 times. np.ones of size 100 is going to give me 1s 100 times. So whatever n is, I can build this, this, and that. Okay? All right, so now, how can we do, there's no numpy.-2s. There's no numpy.2s. All you need is numpy.ones, because you can multiply that by whatever value you want if you want to get a bunch of -2s or -5s or -3.2, right? So all you need is numpy.1. So how do I get the -2s in the main diagonal? I simply say my main diagonal is -2 times numpy.ones of size 5 is going to give me -2, 2, 2, 2, 5 times. So that can take care of this, for example. Now there's still one issue. I need to fix the first and last points on the main diagonal, or last point on this diagonal, or the first point on that diagonal. Remember forward and reverse indexing. So let's start here. My main diagonal, let's say, is of size 5. It's mostly -2s. So -2 times numpy.ones of size 5 gives me -2, -2, 5 times. Then to fix the first point, this array, numpy array, the first entry, which is d at 0, I set it equal to 1. So it's going to change this to 1. So I get 1, minus 2, minus 2, minus 2. I still need to fix the last entry and turn it into 1. So I index from the back. D at minus 1 is also equal to 1. I set it. And then I get a 1D array representation of this main diagonal. This 5, you put any number here, it will reproduce this over and over again. So what I've done is as if I've taken any one of these diagonals and made it into a flat 1D array. The next step is going to be and take this and put it back on the diagonal. Okay? So that's the first step. And we'll do this in a bit once we get back to Python. But this is what the code would look like. From numpy, import 1s, and n equal 5. This is the only thing that the user is going to care about. Because this could be 100, 5,000, whatever you want, number of grid points. Then d is minus 2 times, that's the main diagonal, minus 2 times 1s of size n. So it's going to be minus 2, minus 2, minus 2, n times. Fix the first point, fix the last point, 1 and 1. Then the upper diagonal, I call it u for upper. And then it's also 1s, but of size n minus 1. See how I'm scaling this? U at 0 equals 0 because the first entry on the upper diagonal is always 0, right? And then L, the lower diagonal, is also 1s of size n minus 1. The last entry in the lower diagonal is always 0. So L at minus 1 is equal 0. This works for any value of n. So now we've created each one of these diagonals as a 1D array. Okay, a 1D array. The next step is to combine them and put them in a matrix. So now I'm only focused on the coefficient matrix. If I know the coefficient matrix, I can solve the system of equations. The next step is to combine these 1D arrays to build the full coefficient matrix. There's another routine in numpy, because they've thought about all of this, and that takes a 1D array and places it on whatever diagonal you want in a matrix. Okay? And that is called numpy.diag, for diagonal. So numpy.diag takes a 1D array called v, or vector, and places it on the kth diagonal in a matrix. And it returns a full dense matrix. Okay? What is k? The main diagonal is always our reference in a matrix. The index of that diagonal is 0. It's the 0th diagonal in a square matrix. Is the main diagonal. The first upper, k is 1. The first lower, k is minus 1. Second upper, k equal 2. Second lower, k equal minus 2. You can, now this np.diag creates a full matrix. It takes v and puts it in that matrix. Okay? So let's actually do this together now. We're ready to do this together. Let's go back. Let's go to Python. And I have the example for you on the slides. So I just want you to follow with me in your code. And then you'll have this also in the slides for you. All right. Okay. Let's do. So n is equal 5 number of points. And I always like to start with a small number because when I print, I want to see everything. When you go to larger numbers and you print something out, it's not going to. So everything is recorded. Don't waste your time taking pictures, low quality pictures and whatnot. These are on the slides. They are recorded on your YouTube. You can see them. Just focus with me, and I'd rather you code with me than have the urge to feel like you want to take a picture because you want to preserve this for eternity. It is on YouTube. You have the slides with you. Just work with me here. So I always like to start with a small number because I can see things that are easy to think about, okay? But if you put n100 and you print it, it's just going to give you 3 dots because it cannot fill the page with a matrix of 100 by 100. Make sense? Once we are sure that things look correct, then we'll go to larger numbers. All right. So I said I'm going to build now the main diagonals. So my main diagonal, I'm going to call it MD, is minus 2 times mp.ones of size n. Print main diagonal. Okay, it's minus 2, minus 2, minus 2, minus 2. Okay, so now let me show you that, how this works. MD at 0 is 1. Print MD. Okay, so initially we started with minus 2 5 times. Next we change the first entry. Now it's 1. And then we can change the last entry. MD at minus 1 is equal to 1. Print MD. So now I have 1, minus 2, minus 2, minus 2, 1. That's what I want my main diagonal to look like. Okay, going to get rid of printing. All right, now upper diagonal, let's call it UD. It's mostly 1s, so MP dot 1s of size n minus 1. Be careful, n minus 1. Okay, and then for the upper diagonal, oh, crap, I forgot. What do you do? Well, thankfully, you wrote the matrix in the system of equations already by hand, or you typed it in your notebook or somewhere so that you know what you're working with. So I can go back to this. I'm teaching you good habits. Okay, right? So I have 0 here, and it's all 1s everywhere else. Okay? So the first entry in the upper diagonal is going to be 1, and then I'm going to print my upper diagonal. My upper diagonal, oh, sorry, the first entry is 0. My upper diagonal is 0, 1, 1, 1. Great. And then my lower diagonal is also MP dot 1s of size n minus 1. And the last entry in the lower diagonal, so LD minus 1 is 0.0, and print LD. Okay, it's 1, 1, 1, and 0 at the end. So if I go back to my notes, this is the lower diagonal. 1s, 0 at the end. This could work for whatever you want, whatever size n you want. It will just work. If I put n 15, it just does it. Okay? Doesn't matter. Let's keep n equal 5 for simplicity. So now I want to illustrate to you how diag works. And I'm going to start only with the main diagonal. Okay? So MP, if I do MP.diag, you open and you look for this, it extracts or constructs a diagonal array, and it just returns a matrix. Okay? Let me show you this. So if I do np.diag with my main diagonal and my k equals 0, so I'm putting the main diagonal on the matrix, it's going to return a matrix of size 5 by 5, because this is the main diagonal. I put it on the main diagonal. So if I look at that, it took the 1 minus 2 minus 2 minus 2 1 and put it on the main diagonal, and I have 1 2 3 4 5 entries, 1 2 3 4 5 rows and 5 columns. Okay, I can take the main diagonal and put it on the first upper, but that's going to result in a 6 by 6 matrix, right? So I can do that. Look, I can do k equal 1, but that would be wrong. That would be a different problem. So it put it here 1 minus 2 minus 2 minus 2 1, but now my matrix is 1 2 3 4 5 6 by 6. Okay, because this main diagonal for our problem doesn't belong here. Okay, so I'm going to go back to k equals 0 here. Okay, now the same thing occurs, the same thing happens for the upper diagonal, except k will be 1. So we can do np.diag for the upper diagonal and k equal 1. It's going to return a matrix 5 by 5 still, but the first upper has 0 1 1 1, which is exactly what I expected, 0 1 1 1. Okay, so this, it does that, does for the lower, but I need them all together in one matrix. What do? Just add them, exactly. Thank you. Because numpy operates pointwise, element by element. This is an numpy array, this is an numpy array, the lower diagonal is an numpy array. If I add them and they're all the same size, it's going to add element by element. If they're not the same size, it's going to vomit at you. It's going to be like, I don't know what I'm doing, okay? And you'll know the error then. Okay. So all I need to do is add plus np.diag, my upper diagonal at k equal 1, plus np.diag, lower diagonal at k equal minus 1. Now when I print it, like this beautiful matrix here, 1 minus 2 minus 2 minus 2, 1, 1, 1, 1, 0, 0, 1, 1, 1. That's exactly what I was expecting. Okay. I'm going to call this, I'm going to bring this back up here. And I'm going to call this A, or coef matrix. Okay, and you can say print A here. Okay, great. Will this scale? You bet. Let's go 15 points. Look at how beautiful this is. 1 minus 2, 2, 2, 2, minus 2, minus 2, minus 2, 1. 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 0. Will it go to 100? Absolutely. Will it go to 1,000,000? Absolutely. Because we grabbed that structure of the system of equations and turned it into code. These are just few lines of code. That's the beauty of programming. Do 100. Oh, you're going to get 3 dots. The 3 dots. You won't be able to see the whole thing. Okay? Let's go back to just 5 points, because I'm building this together. Okay. So let's see where we're at here. Okay, so I have the code here for you. And then finally, oh, there you go. We're going to do this together. We have everything we need to build this. We know how to build the coefficient matrix. We just did it together. Next, to solve this, I need to build the right-hand side. And the right-hand side had the boundary conditions, so we need to define those, t left and t right. We're going to come up with those, whatever we want. And I'm giving you a source term here, alpha e to the minus x minus a over sigma squared. This is a Gaussian distribution located, this is a heat source located at A. So if I want A to be in the middle, I put it at half. If you want it here, 1/3, 2/3, whatever I want the heat to be, source to be. And sigma is the standard deviation. It's how wide is that heating? Okay, how wide is that heating? All right. So let's go ahead and do this. Before I do anything, I'm going to come back here to my source term. Okay. And I'm going to say, to clean up my source term a little bit, make it a little bit, okay. So alpha, remember I wanted to put alpha e to the minus x minus a squared, etc. Okay. So, and I can type alpha like this and say this is, you know, whatever, 1 e to the 6. I've played with these values before, so I kind of know what to expect. Or you can put alpha, backslash alpha, and press tab, and it turns it into a Greek symbol. Advantages of using this is that you can be faithful to the math that you wrote on your notebook. The disadvantage is that alpha is not a searchable symbol. It's not just your standard alphabet. So be careful. I would just stick to writing it as alpha, A-L-P-H-A. It's up to you. Okay. This is not every time you have to put the, okay. So let's put alpha equal, and then sigma equals 0.1. And we'll play with these numbers a little bit. And I want to put this in the middle, A to be, I want A to be L over 2. Okay, so right in the middle. Okay, and I'm going to return alpha times np.exponential minus x minus a. And I need another parenthesis here, because I need to divide by sigma, right? And then all of that is, actually I can do it cleaner, minus x minus a squared over sigma squared. Okay, I'm missing out a parenthesis here. Okay, this is consistent. Okay, this is my formula, alpha e to the minus x minus a squared over sigma squared, alpha e to the x minus a squared over sigma squared. Okay. Now, who has not done plotting in Python? Okay. You've all done plotting in Python, so you know how to plot this? Yes, 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 I saw her. Okay, okay. So to plot a function in Python, we need to plot it discretely at discrete points. We can't plot a continuous function like we do in math. You need to evaluate the function at a bunch of x values. So you get the y values and you put, and then Python is going to put the y values for you up there. Now, how do we get x values? Well, thankfully, we already had a linspace defined. So if I want to plot the source term, see how it looks like across that heating rod or the heated material, all I have to do is apply my source term to that array, which we need anyway, and then plot that. We're just going to plot an array. To plot in Python, you need matplotlib. So we will do import mat, so matplotlib dot pyplot as plt. Just do it like this. This is pyplot. It's a Python plot from the matplot library. It's just defined like that. I always import it like this, and like whoever first wrote this on the internet, and everybody does it the same way. So we just import it like this. I call this my boilerplate, that header cell in all my notebooks. I copy and paste it in each and every notebook I use because it's the same over and over and over again. Okay, so we're going to import this from matplotlib. Okay, and this is my source term. So now I already have source xi over here. I'm going to remove it. To plot something, you have to do plt.plot, and then you open parentheses, and it tells you plot bunch of arguments and whatever. You can read all of this, but you don't need any of this. All you need is plot x, comma y. Y, x are the x values, the independent variable. Y is your y values, your function values. So here I want to plot my xi on the x-axis because these are the discrete points on the rod. Okay, and I want to plot my source at xi. And if I do this, it's going to give me something looks like this. It's connecting it by lines, which is really wrong because I only have the values of the source term here, 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 and here. But as I increase my number of points, so if I have, so I'm going to put my n over here, put 100 points, and I'm going to put n over here for my linspace. I'm going to delete this. So now my plot is going to look much nicer because I have more points, right? I have more points to evaluate the source term. And indeed, it looks like, oh, there's a lot of heating occurring in the middle, okay? And then it kind of dissipates away. So you can play around with the parameters. So if sigma were larger, 0.15, what's going to happen? That Gaussian is going to widen, right? It's going to get wider. You see how it's widening and widening. So you have a bigger torch. You're heating more of the material. Okay. Hello. Okay. Now if I shrink this 0.05, it's going to be narrower and narrower. So you're targeting with laser precision. You're heating it at a very small interval. Okay, and you can move the location of the heating. So let's say at 1/3, that moves it at 1/3 of L. Or you can move it here, or you can move it over there, whatever you want. Okay, or you can put it at 0.8. Okay, then it's going to put it over here. Okay, so where are you centering the heating? So you can play around with all of those. We're going to keep it at L/2. Okay. Now, if you know me, what am I going to say next? Pardon me? Sure, I put a grid, but what drives me crazy, if you're like standing and doing your proposal defense or your qualifying exam in front of me in a couple of years, what am I going to burn you on?
The X, Y, not labeled.
Okay, that too, but I'm not going to label it here for simplicity. You obviously should label, put a grid where needed. Ariana? Yeah. This is really bad quality plot. You are not living in the 50s where you have to draw your plot with ASCII art. You have access to powerful, good, beautiful graphics. There's no reason you produce a crappy graphic like this. And if you can't tell that this is pixelated, you should be able to see it now. Whereas compare this to, oh, look, why can I zoom in here and like everything looks clean, or here, right? How can I zoom in here and everything looks clean? Okay? So I'll teach you this in your intro to research on September 30th. But very roughly speaking, this is the difference between two types of graphics, what's called vector graphics and what's called raster graphics. Raster graphics is the bitmap style that used to predate a source of graphics where you take a pixel and color it, and you return that. So what matplotlib is doing here, oops, it's taking pixels on the graph, coloring them, but when you zoom in, it's gonna try it's not gonna redraw those pixels because it already set those pixels at over here at this resolution. What we want is vector graphics. What are vector graphics? Vector graphics redraw themselves every time you change your resolution or you zoom in. Okay, so notice as I zoom this in, for example, and then it takes a second and it redraws it, right? And then it redraws it. A font, for example, in your Word document, in your Google Doc document, is a vector graphic style. It redraws itself every time at any zoom level. So if I'm creating this plot, this is not a picture I took with the camera where I have a finite resolution from the camera. I should be able to have infinite resolution here because I'm plotting this. So I want to tell Python to do this the right way and give me vector graphics. This is an absolute must for anything. For my undergrads, I used to tell them, it's okay if you put this or not. For grad students, it's an absolute must. We will not accept a low quality graphic unless the source itself is a low quality. Like you had to grab a paper from the 20s and you took a picture of it and you're stuck with that. But if you're creating a fresh plot, it needs to be high quality. It needs to be, if you can do it vector graphic, it needs to be vector graphics. So here's the trick. Matplotlib inline. So do this, and then config inline. Don't ask me why this is the way it is. Equal SVG. What I'm doing here is I'm telling Python, for anything for matplotlib, put my figure format as SVG. What is SVG? Scalable vector graphics. It's a scalable vector graphic. So then what it does, it's going to turn every figure you create with Python into a scalable vector graphic. So let's see. I run this again. Aha. Now, if I zoom into this, look at that. You can zoom into whatever level I want, and it will look beautiful and great. Okay? Okay. Little tip. Use it all the time. When you export this figure, don't go take a screenshot, because when you take the screenshot, it's going to limit you to the resolution of your display. And if you have an old laptop at 800 by 600 pixels, you're going to get an 800 by 600 pixel resolution. And when you send it to me on my Retina display 5,000 pixels, it's going to look like this. It's going to look horrible. What you do, you export this as a PDF. Not even a JPEG. JPEG, GIF, all of these are raster images. You export this as a PDF because PDF is a vector graphic format. When the source is vector graphics, it will be vector graphics. Okay, I'll talk a little bit more about this in Intro to Research when the time comes. But for now, do this little trick and you'll be good to go. Okay? Okay. So now we've done this, and of course, what your colleagues said, you have to label the axes, you have to put a grid when needed on the plot to make it. I'll also talk a little bit about this in Intro to Research. If you don't know how to do this in Python, just Google it or go to GPT. Hey, help me. How do I create a label? Here's what I did with my plot. How do I create a label? How do you create a grid? Just simple, and you move on. Occasionally, I'll do a grid. So if you do plt.grid, it just gives you a grid here. And if you do plt.x label, and say position in meters, okay, and plt.y label source term, okay, source term, okay. I can understand this now. All right, this is great. So now we have our source term. We have set this up. So from here onwards, what I would do if I were you, this is called my boilerplate. Whenever I start a new notebook, I copy this and put it in the first cell. So I don't have to worry about it, remembering it. And then you'll have, within a couple of years, every notebook you have on your computer will have this. So if you lose it, you just open any notebook, grab it, and put it in any new notebook. I could never remember this, by the way. I just always copy it and paste it. OK. So now we are ready to get to our solution. What we have not defined yet. So I defined my n, my number of points here, because I need it for my lin space and my source term. I also need to define my temperatures. So I'm going to do that here. So my T0 or T on the left or T at x equals 0, let's say this is, let's put it at 500. So, oops, temperature in Kelvin at x equals 0. And T on the right is, let's call it T0, and T on the right is equal to 200. So temp in K at x equal L. Okay, and my heat conduction coefficient, thermal conductivity, I'm just going to start with a value. I'm going to start at 300. Then once we have a solution, we'll start changing that K to test what we talked about. If K is large, it's going to allow heating to spread quickly. If K is small, it's going to prevent it from spreading quickly. Okay, but I just want to get to the solution now. Okay, so this is great, and I got my coefficient matrix built up. I need to build the right-hand side next. Okay, build the right-hand side vector. So right-hand side vector is simply, my right-hand side vector is mostly minus delta x squared times si over k, except for the first and end points. That's great. So then what I'm going to do, I'm going to say b is equal minus dx times dx times my source term at xi over k. But I didn't define my dx. Well, I can get it from here. My dx is simply the difference between two consecutive points in xi. So it's xi1 minus xi0. And then I can print dx. Does that make sense? Because this is an equally spaced list of numbers. The difference between any two consecutive points is going to give me the spacing. Could do x2 minus x1, x5 minus x4. It's the same thing. So now we go back. This is minus dx squared times my source term at I over k, exactly as the math says over here, minus delta x squared times si over k. Now this is going to return an array of values, b0, b1, b2, etc. And each value is going to contain minus delta x squared s1, minus delta x squared s2 over k, and so on and so forth. I still need to fix the first point, b0 is equal to t0, and the last point, b minus 1, is equal to tr. Agreed? Because the first point in b is t0 or tl, and the last point is tr. Okay? I guess I can call it tl here if I need to. All right, finally, we're ready to solve. Finally, solve the system of equations. Okay, T, or my solution, my temperature, is mp.linalgebra.solve a comma b. And it did it. What do we do next? We're going to plot it. plt.plot Where does t live? It lives at the xi values. So on the x-axis, I'm going to put the xi values. On the y-axis, I'm going to put my solution. plt.plot xi t, and it did something. Okay, we'll talk about this on Thursday. But roughly, what I'm looking at here is my temperature distribution with a 500-degree temperature on the left and a 200-degree temperature on the right. Looks like I'm capturing my boundary conditions correctly. Then there's some heating here in the middle. It's not strong enough to raise the temperature above 500. We're going to manipulate that a little bit by changing K, by changing the strength of the source, of the heating source, see how that curve changes. Okay, we're going to change later the temperature. We're going to do some sanity checks to make sure that we got this right. What happens when K approaches infinity? What happens when K approaches 0? What numbers are we going to get? Is this all going to make sense? But that's how you do it. Okay. On Thursday, we'll continue from here. Review anything in the lecture. If there's anything iffy, repeat it, and please ask questions. Come to the help session. We're gonna keep moving. Okay. Thank you and Godspeed.